Good afternoon, judges. My name is Tarun Bachu, and I'm coming to you from India today. I'm going to try my level best to present, but I hope you don't mind about the difficulties. I'm an incoming freshman at Liberty High School who's passionate about engineering solutions to modern problems. My venture tackles one of, if not the world's largest global issue, climate change. With climate change being such a broad subject, I want to fixate on a smaller component, the gases emitted from smokestacks, specifically capturing all harmful gases, opposed to just carbon. These gases include nearly 45% of total emissions, including nitrous oxide, sulfur dioxide, and of course, carbon dioxide. The exponential rate at which these gases have grown within the atmosphere is unsustainable, which is where my device kicks in. ASCaged, an acronym for an efficient solution to carbonic acid gas and its environmental desires. I first looked for current methods being developed across the world to improve these searches. Unfortunately, I found that these methods, which consist of carbon capture plants/technologies, have three major limitations: machinery cost, efficiency, and environmental friendliness. Carbon capture plants can cost upwards of $500 million per unit, while others are inefficient, only targeting around 3 to 5% of total emissions and are hardly sustainable. My device ASCaged uses multiple novel technologies, and in turn addresses these flaws by being cost-friendly, sufficient, and easy to install in factories and plants. I said earlier, the emissions immediately activate the perpendicularly aligned ASCaged pods via diffusion. Within each pod being this visual, there is a certain content of liquid carbon disulfide dispensed in a vapor form initially. Here's a video of me experimenting with carbon disulfide at a liquid state. This shows the scientific experimentation, and I'll be talking to you about the engineering. In each device of ASCaged, there are not 1 but 8 pods, of which 5 are always activated, with 3 pods on standby. These 3 pods are activated accordingly through a thermal detection system, or a temperature-dependent algorithm. In this thermal detection system, a SparkFun A4 thermal camera collects a thermal and pressure input into stage of pod 5, the last auto-activated pod, and transmits that thermal input to a TNZ 4.0 microcontroller, which in turn lights up the given NeoPixels, currently only for display. In real life, the system will collect data in 9-second intervals, and use C++ code, the very same as used in elevators. I said earlier, the liquid vapor droplets condense and combine with the pollutants, thus turning the pollutants themselves to a liquid state. These liquids are transported via large pipe systems to industrial refrigerators located around the premise of the plant, for 2 possibilities: being recycled back into the pod for subsequent condensation cycles, or simply the disposal of the pollutants, or the excess pollutants. The temperature before condensation is negative 95 degrees Celsius, and the temperature after condensation is negative 35 degrees Celsius, which are ultimately recycled back into the pod. Up to 30% of my device can be powered by heat flux-based TEGs, while the remaining is compatible to be powered through other renewable or green strategies. ASCaged should drop the cost less than 1% of current methods, being only $475,000 per unit, or to automate an entire factory, with an additional daily maintenance of approximately $50 per day. My iterations for the device are threefold. First, subsequent cycles. Second, the thermal detection system. And third, my piston system. Just earlier, I talked about the smoke, or liquid vapor droplets, combined with the pollutants, and it ultimately recycled back into the device. But what about the initial procedures? Since there is no smoke that's been collected thus far, there's also none to recycle. To develop this initial cryogenic liquid, I expected liquid carbon to be finalized, because of its efficiency in abundance, compatibility, and boiling temperature. But due to the honeycomb lattice phenomenon of carbon, I finalized that I'd have to implement another cryogenic liquid. I'd researched liquid argon, liquid hydrogen, liquid nitrogen, and even liquid air, but I found all of them to be ineffective with either the cost or the boiling point. At this point, I circled back, wondering if I could use another gas that studied a lot, liquid sulfur dioxide. This was the biggest unexpected outcome of my project. The reaction between liquid carbon and liquid sulfur yields carbon disulfide, an endothermic reaction of approximately 50 degrees Celsius, assuring the condensation of any temperature of gas or smoke entering ASCaged. This is iterative on the scientific level. Moving forward, I've also built a piston within my device to lower atmospheric pressure, using ideal gas formula and Gay-Lussac's principle. In addition, I made the piston to be hollow, doubling as an egg system, and I faced several hurdles in determining the ideal diameter. At the beginning of my presentation, I've also talked about the deployment of additional pods to accommodate for higher temperatures, 3 to be exact. I'd first believe an app of some sort would be sufficient with Bluetooth connection, but I labeled Bluetooth as inefficient, as after understanding that the distance between the user and the device may span several hundred meters. I then moved to a thermal detection system, where I developed 2 simple circuit boards before moving on to my final iteration. As mentioned earlier, with the TNZ 4.0. This was iterated on the engineering level. After analyzing the current industrial market, I've designed ASK to operate with over 95% of smokestack designs in factories and plants. The industrial market for my device is large, and aims to be even larger in the future. A 2019 study stated that over 90% of factory managers and 85% of business owners find interest in going green, if methods fall under 5% of annual revenue. With both sides of the story shining, I believe my device has a great value proposition and is feasible in today's environment. My device ASK is a novel and original CCS or carbon capture system that works for all pollutants. It is efficient in condensing all harmful gases. Global warming is an issue of today, as is climate change. But ASK can be the solution of tomorrow. This is my bibliography, this is my logbook, and here are my visuals. I want to thank you guys for listening to me today, and have a great rest of your day.